second thing is, now I took this program, took the dual of it, I got this. But now this is also a linear program. So there should be a dual of it. If you take the dual of this, you will get this. How you take the dual of this? So one way is you convert this into standard form, then you know how to take the dual and do 1000 things. But the better way and the way in which you should always take the dual is keeping these things in mind. Okay? So let's take the dual this way again for this. And you should be awake and help me out, otherwise we will do some mistake. And then you will be staying here for much longer than you want. Okay? So Y transpose A less than equal to C. This means how many equations are there? N. Right? Now I need to multiply. Question? No. Okay. I need to multiply each of these equations with a constant, right? So that I get something which is sorry? Depends, is your C a column vector or a row vector? Okay. So, okay, let me do this. Okay, sounds good. Y1 A11 plus Y2 A21 Ym Am1 should be less than C1. Okay? That you cannot, I hope, argue. Right? Okay, good. Now, so if I want to take the dual of this, how many variables do I need? Because there were m equations, right? So I want to maximize something which is going to be a function of x. There will be such that, and then condition on x. So first thing, this is a minimization problem. That means I want a lower bound, right? So the linear combination should give me something which is less than the linear form here or bigger than the linear form here. Exactly. So that means we need equality. We need to get this linear form exactly. If I get a higher value than this, it's not going to happen. I will not get a lower bound. If I get a linear form which is smaller than this, still it's not going to tell us anything, because y1, y2, y3 are all reals. So I should get equality in the constraints. Equality in the constraint. Depending upon what is your variable, the sign of the constraint will be decided. So I will get, and now remember, this is less than equal to C. Right? So what will be the value if I am multiplying everything by x? I will get C transpose x on the right hand side. So I want to, my lower bound is C transpose x. The value of the linear, like it was B transpose y, right? Because x1 multiplied by c1, x2 multiplied by c2. This will be my 15 or whatever I came, right? That would be x1 times c1, x2 times c2. So C transpose x, right? What is my constraint? x1 times a11 plus x2 times a12 plus xn times 1an should be this. Okay, one small thing, what should be the sign of x? X is a variable in my primal. That means its sign will be decided by the constraint in the dual. So now, if you think about this, if I multiply, so what will happen? If I multiply with a negative thing here, the sign of the equality will be reversed. I want whatever I get, I want C transpose x to be less than B transpose y. And that will only happen if I multiply the inequalities with a positive thing. So I want x greater than or equal to 0. Because you want a lower bound. That is the whole premises. Now this is a minimization problem. It's easy to give upper bound, you want to give a lower bound. So how do we get a lower bound? Yes. And the easy proof that it is upper bound, lower bound or whatever is this chain of inequalities. Let's say x and y are feasible. Dual respectively, right? So now you have B transpose y or right, this is just fine, right? And then B is Ax for some x. And this y transpose A is greater than C. And this inequality will only happen because x is greater than or equal to 0. No, I'm saying for this to work. From here also, if I had multiplied by something negative here, then the sign of the equality had to be reversed, right? Then this linear, then whatever linear form I am getting, it won't be less than C transpose x. See, it's the same calculation which is I am doing here. When I am multiplying by x, I want when x multiplied by this quantity, it has to remain less than C transpose x. That will only happen if x is positive. And then that compared with B transpose y. Right? Okay, so this is basically the thing which is going on, right? So again, this is because of primal variable or dual constraint. This is because of dual variable or primal constraint. and this was all pretty cool because Ax was equal to B. And that's not going to happen in the next example. I'm going to make your life more difficult. Now even this is going to have inequality or equality, right? What is the dual? This dual? Not. You're not going to get this dual. You're going to tell me what dual you're going to get. So now one way is, again, you can start multiplying everything, right? But the easier way is, the dual is going to look like this. You have to figure out the sign here. You have to figure out the constraint here. That you can remember by doing this thing, that how should the sign change. First, let's try to fix up the sign here, right? So if I want the sign here, that will depend on the sign of the, yes, this side, which what? Constraint. So it should depend on this, right? I want an upper bound, right? That means B transpose, whatever comes here, that linear form should be less than B transpose Y, right? Because I'm going to say C transpose X less than my linear form less than B transpose Y. Right? This is going to be my argument. I'm going to multiply these, get something which is higher than this. And then my argument would be, oh, C transpose X is less than equal to that term, and that term is less than equal to B transpose Y, so B transpose Y is an upper bound. Now for this to happen, Y should be I want Y transpose Ax to be less than Y transpose B. That will happen for which Y? Negative. Y transpose Ax less than B, because you are going to give this argument for your duality. This is your argument to duality, right? This is a condensed form of duality which you were doing, right? Writing down equations, multiplying. This is the linear form which you get. You multiply your constraints with variables of the dual, and then you apply this argument, right? So then you want Y transpose Ax to be less than Y transpose B. So this tells us Y less than equal to 0. Now you are worried about this side. Okay, now you want to say C transpose X should be less than Y transpose Ax. This sign will be determined by the sign in the primal variables, right? This sign with the primal variables. So if I know X to be greater than equal to 0, and if I want this condition to be true, what relation do I need for Y transpose A and C? Yeah, so if X was greater than equal to 0, then I would have want Y transpose A more than C. But X is less than equal to 0. This is your dual. Okay, minimum B transpose Y, Y transpose A less than equal to C, Y less than. Okay. So this gives you a generic way to take duals. Write something like this, write the maximization problem, minimization problem, the questions are signs here and here, and that sign you can determine by looking at what you want to do. This is what you want to do. You want to create a linear form which is an upper bound on primal value, which is a lower bound on the dual value. A linear form which is a primal, I shouldn't say it a linear form because it's a linear form with respect to x if y is a constant. It's a linear form in terms of y if x is a constant. So I don't know, quadratic form. You want to create this quadratic form which is less than the dual value but more than the primal value. And if you want to keep these, that will easily tell you what signs to put. But again, the amazing part is there exists a y such that y transpose b is going to be equal to c transpose x. Strong duality holds. But wait, that's not true. So yes, so let me talk about the technicality, but we know this, right? Primal dual, how to create these. The constraint here corresponds to variable here, the variable here corresponds to constraint here. Now let's talk about the technicality. You remember the technicality? What if this is not feasible? Okay? So now let's think of it this way. If this is unbounded, right? If this is unbounded, then clearly there cannot be any upper bound. That means dual is going to be infeasible. If D is unbounded, primal will be infeasible again by the same argument. If this is unbounded, there cannot be a lower bound. There cannot be a lower bound, there cannot be a feasible solution here. The most interesting case is P and D both are feasible. In this case, opt of P equal to opt of D. Okay? If infeasibility is taken care of, then the values are equal. This is the strong duality. Okay? Is there any case remaining? Yes. What do you think? Okay, let me not keep the suspense. I don't have any intuition about this. It turns out there are LPs where both are infeasible. If you are very, very curious, do Google search for Rajat Mittal, CS655, course notes, duality, you will see an example there. Okay, so yes, both programs can be infeasible. But again, 1, 2, 4, this is the least useful. These are the cases which needed in the haystack. You really have to dive deep and find cases. Oh my God, both are infeasible. For any natural LP, 99% probably whatever percent more than 99.9999%, you will be in this case. There are very few cases where these happen. But this I have seen in my life. This I have constructed for lecture notes. Okay, but this is possible. Sounds good? So now we are going to see what this kind of equation gives us. First thing is equality can hold, that is strong duality. But if strong duality holds, that means everything is equal here, right? If everything is equal here, it tells you a lot about the primal and dual optimal solutions. That is called complementary slackness. And we will talk about it. So once again, in case this is, so if there are x0 and y0 for which this side is equal to this side, then everything has become equal. And if everything has become equal, there is very nice relation, there are properties of x0 and y0 which we can infer from that. That's called complementary slackness. This is the topic for next class. Thank you.